Hi everybody, the next thing to talk about is water and pH because pH is pretty important in biology and I would be remiss not to talk about it. pH is a measurement to detect how acidic or how basic a solution is. It stands for potential hydrogen, so in essence it's really the amount of hydrogen ions that exist in a particular solution. So in order for us to discuss exactly what being acidic means or what being basic means, like what makes something basic and what makes something acidic, we have to really look at how ions can dissociate in water. So this reaction here shows two water molecules that are bound by a hydrogen bond, and what can happen sometimes is this hydrogen ion can dissociate and get pulled off of that water molecule and attach to a neighboring water molecule, such that the resulting products of this reaction would be a hydronium ion, which has 3 hydrogen ions instead of the normal 2, and a hydroxide ion, which just has 1 hydrogen ion. The chemists have simplified this equation by just canceling out the water molecule here and the water molecule here to get the reaction that's shown below, where we just have one water molecule that dissociates into a hydrogen ion, which really represents the hydronium ion, and the hydroxide ion here. So water, when this takes place in water, hydrogen ion won't exist by itself. It always will associate with another water molecule to produce a hydronium ion. You won't just see a hydrogen ion just swimming around in water by itself. It always will be attached to another water molecule. Alright, so I want to bring this reaction back at the end of the video and tie the importance of this reaction to pH. I'm sure that this pH scale does seem somewhat familiar to you, especially if you've taken biology. And like I mentioned before, pH refers to the amount of hydrogen ions in a solution. And as you move closer to 1, the system becomes more acidic. And this means that there will be more hydrogen ions present in the system. And as you move towards a higher pH, then the system will become more alkaline or more basic. And that means that there will be less hydrogen ions present in the system. So let's look at some common household items that you are familiar with, and we'll talk about each of these items, starting the most acidic of these solutions. The first one that's shown is a pH of 1 is hydrochloric acid. Hydrochloric acid is found in your stomach, and you need hydrochloric acid to help break down protein. The next up would be lemon, and lemons have a pretty sour taste, and if you think about the acidity of lemons and vinegar and then tomatoes, you can associate a very sour taste to them. And anything that usually is sour has acidity to it. So that's one way you can associate something that's acidic, is that it has a sour taste. The next up would be bananas and potatoes, and then we have water, which is pretty neutral, and eggs. Next up will be baking soda, soap, and then we start seeing the cleaning solutions here. There's soap, ammonia is at 11, we have bleach, I believe that's oven cleaner, and this solution, it's not really labeled on this scale, but I imagine that it's sodium hydroxide, which is a pretty basic solution that chemists frequently work with. So looking at this scale, you can think of things that are acidic having a very sour taste, and things that are basic having a very bitter taste to them, actually. And coffee would run around this scale, so it would be around 7 to 9, and coffee, as everyone knows, is pretty bitter. Okay, so the next thing I want to talk about is the pH scale, and how this scale is what's called a logarithmic scale. What that means is that it's not a normal type of scale where each whole number just goes up by one value. It is going up by just one whole number, but really when you're moving up or down the pH scale, depending on where you are, that with each jump, it actually means that you are jumping by a factor of 10. So each whole value in the pH scale is different by a factor of 10. And I can't emphasize that enough, because even though at first you might seem that's not a big deal, it is a really big deal. It's emphasized a lot in chemistry and in biology, because if you were to look at a system and it differed just by a little bit, like even your blood pH, if it went down or up by one whole value, you could die. And it could become very toxic to your system because you're going up by 10-fold or you're going down by 10-fold. So each whole number jumps by a factor of 10. And that's something that I want to emphasize. And as you are moving towards 1, you are increasing in acidity, but if you were moving towards 14, you would be increasing in alkalinity or becoming more basic. And that would mean that the smaller the number, the more acidic, and the larger the number, the more basic. So smaller pH number would mean more acidity, which also would mean higher hydrogen ion concentration. And the bigger the number in pH, the opposite would be essentially the reverse. The less acidic and the more basic and the less hydrogen ions. So the more acidic a solution is, the more hydrogen ions it will contain. So what I did in this next slide is I took this scale and I flipped it vertically. So we have the scale going from 1 to 14. And I'd like you to take a moment and look at this scale and see if you can notice any patterns with this particular scale. Like as you're moving from 1 to 14, what do you notice with the hydronium ion concentration? So take a moment and just study this scale, and we will discuss what this scale is indicating. Okay, so I hope you did actually take a moment to look at this scale and study this slide for a bit. What this is saying is as you are moving towards 14, so if you were to look at this, the way that I've oriented it, as you're moving down the pH scale, so it's just the way that I've oriented this that I'm going to say down for this case, but as you are moving down the pH scale with the hydronium ion concentration in the solution, it is actually going down, right? Because it's getting less and less and less. So we actually see more hydronium ions at a pH of 1 and less of it at a pH of 14. So the definition of pH, the true definition of pH, is that it is it stands for potential hydrogen, but what does that mean? So pH is the negative log of the hydrogen ion concentration measured in moles. Okay, so the pH of, say, 7 would mean the negative log of 7, which is 1 times 10 to the negative 7. So remember, the log of anything, if you've never heard of a log, then it means 1 times 10 of a particular value. So it's that factor of 10 that we discussed, that each whole value as you're moving up or down the scale is different by a factor of 10. So a pH that has a negative log of 7, which is 1 times 10 to the negative 7, really means that pH is equal to 1 divided by 10 million. But then you might be asking, of what? What is this actually measuring? Well, I mentioned it before. It's measuring, going back to this equation here, it's measuring the moles of hydrogen ions. So let's go back to that first equation that I showed you at the very beginning. So imagine this equation here, where we have two water molecules, one hydrogen ion dissociating to produce hydronium ion. What this equation now is saying is that in a pH of 7, this reaction takes place 1 out of 10 million times. In a solution that is a pH of 7, such as water, this reaction doesn't take place that frequently, but it does take place 1 out of 10 million times. Stop and think about this for a bit. What would this mean if we were looking at a pH of 1? How frequently does this reaction take place in a solution that has a pH of 1? So I hope that you thought about this, and the answer to that would be 1 out of 10 times, because a pH of 1 means that this reaction takes place 1 out of 10 times. So this takes place pretty frequently in a very acidic solution. And that would mean that hydronium ions would exist in higher concentrations. So hydronium ions are pretty corrosive, and they break down tissue pretty fast, and that's why acidic solutions can be very dangerous. But very basic solutions are also known to be pretty dangerous as well. All right, so just kind of summing up what acids and bases are. Acids have a high amount of hydrogen ions. They have a lower pH, and it's usually less than 7, and they also have a very sour taste to them. And I made the font color red here is because chemists often associate acids with the color red, and bases are often associated with the color blue, where in bases you see a low amount of hydrogen ions, we see an increase in the pH, and usually that pH is greater than 7, and it tastes pretty bitter. Alright, so this is my environmental plug. This is the measurement of hydrogen ion concentration in rain that precipitated from the atmosphere in 2010. And as you can see, if you take a moment, the color indicates the pH, or so that a color that's closer to red means that it's a lower pH, which means that it's more acidic. And if you get closer and closer to the East Coast, you see that there's more and more acid rain. This is due to the burning of fossil fuels, where we are increasing the amounts of sulfur oxides and nitrous oxides into the atmosphere. And these chemicals frequently react with water to produce hydronium ions. and that hydronium ion, like I mentioned, is pretty acidic and can produce these strong acids, so when it precipitates onto the land, it can threaten the water quality as well as harm some wildlife as well, which is pretty sad. Okay, I'd like to end it there, so I will see you guys next week, and I hope that was helpful.